Hi, I'm Ben-Yaakov. The title of this presentation is Parallel Connection of Charged Capacitors versus Parallel Connection of Charged Inductors. The presentation covers an analysis of the two cases, and then we'll draw some general conclusions. We'll start off with the parallel connection of charged capacitor. This is a case which is treated in many electrical engineering textbooks or physics books, in which there are two capacitors, C1 and C2, which are charged and having a voltage of V1 and V2. Now, at a given moment, we connect the two, so the charge is passing from one to another. Eventually, the system will stabilize, and there will be a final voltage, which we'll call Vf, which will be the voltage of the two capacitors in parallel. Now, there are many ways to treat this case, and there are many analytical methods that one can use. We are going to use the so-called charge balance method, in which we sort of trace the charges that pass from one to another and the total charge. So we start off with a statement that says that the total charge of the system is Q1 plus Q2. Q1 and Q2 are the charges of capacitors C1 and C2. Now, Q1 will be C1 V1, Q2 will be C2 V2. So we start off with these charges. The connection brings some of the charge from one capacitor to another, and eventually it'll stabilize with a voltage V sub f and a total capacitance of C1 plus C2. So therefore, the total charge is then the product of the total capacitor and the voltage across the capacitors. Now, since there is a conservation of charge, this total charge is equal to the charge at the beginning. So we equate the two here, and we end up with an expression for V sub f, which is the final voltage, which is equal to C1 V1 plus C2 V2 divided by the total capacitance. Now we turn into the aspect of energy. Now, the energy stored in a capacitor is CV squared over 2. So the energy originally stored in capacitor C1 is C1 V1 squared over 2. Energy for C2 is the same way, C2 V2 squared divided by 2. And of course, the total energy at the end is the energy of the combined capacitor, which is C1 plus C2, and the voltage that will prevail after this connection, which is V sub f. So it will be the total C times V sub f squared over 2. Now, we have now an expression for V sub f, and therefore we can calculate the energy by plugging in the expression of V sub f. This is then V sub f squared. This is the total C over 2. Working it out, here is the expression we are getting for the final energy of the system. Well, it depends on V1, C1 squared, etc., and there are some cross terms here. And let's have a look at a very popular case that many textbooks are showing, in which the first one capacitor, C2, has a zero voltage across it, that it is not charged. The value of the capacitances is the same, so they are equal capacitors. And in this case, if I'll plug in for V2 equal to 0, I'll find that the energy after the connection is V1 squared C over 4, which is half of V1C, this should be square, V1 square C1 over 2, that is half of the energy got lost. Well, this is fairly known, and the reason is, of course, the losses which are involved in this transfer. Looking at in a more physical way, or maybe an engineering way, what we have here are two capacitors which are charged. The voltages are different. I'm connecting them, but the circuit has some finite series resistance. Now, there is a current flowing through this resistance, which dissipates energy or power, and consequently, we'll end up with the amount of energy which is lower than the energy we started with. Now, it's interesting to see that if RS is, say, relatively large, we'll have an initial current of this magnitude, which will then go down exponentially because it's an RC circuit. Now, if the resistance is much smaller, the peak current at the beginning will be much higher, but the time constant is shorter, so it will go down shorter. Now, the analysis that we have done before shows that independent on the size of the resistor or resistance of this wire, the energy lost is the same. So it really doesn't matter if it's a large resistor or a small resistor, you sort of lose the same power. Well, you can do the calculation in a different way. You can just look at the RMS current and the resistance RMS of this waveform, and you'll end up with the same result. Now we go to the problem of two inductors. We have two inductors, L1 and L2, with, in the general case, different initial currents, and now they are connected in parallel. Well, in this case, there is no question of charge. There's no charge balance involved. What we have here is the energy of one inductor at the beginning, which is I square L over 2, and the energy of the other inductor, and then they are connected. The question is, what will happen? What will be the final energy? There are a number of ways to do it. To do the calculation or the analysis. I'm going to use what I think is an intuitive and easy to understand approach, which will use a model of a charged inductor. If you have an inductor which has an initial value of a current, you can represent it as an inductor without any current plus a current source, the magnitude of which is the initial value of the inductor current. From the terminal points of view, if you look at the terminals here and here, the two elements behave exactly the same. So this is a model which sort of simplifies calculation, as we will see. So here is the problem we have. We have one inductor, which is now represented as a inductor without current plus a current source. We have another inductor represented the same way. If the currents are not equal, there is a difference. This difference should go somewhere. Well, in reality, it'll go to some parasitic resistance that exists as high as it might be, but there's some resistance, and the difference will actually flow through this resistor. Obviously, the voltage here will go up, and the initial voltage, of course, will be the current times the resistance. And then it'll drop exponentially since it's an RL circuit, and until it'll reach zero. When it'll reach zero, this means that the currents are equal, but there is a closed loop here. So what we will have to see is that one inductor will have, say, current in this direction, and the other one will have current in this direction. So there'll be a loop here of the current, no current in this branch, and this is sort of a short on the inductor, which ideally, if there's no resistance, the current, of course, will persist. Now, the exponential approach is possible, but I'm suggesting here a somewhat simpler way to do it, and because it leads more quickly to the results. And what I'm doing here is that I'm putting a Zener diode, which has a certain Zener voltage here, and this will cause a constant voltage here as long as there is current flowing into the Zener diode. Now, what will happen now with the currents of the inductors? Well, the equation that controls the behavior is this equation, which is basically a representation of the state space equation, which says that the rate of change of the current is V over L, voltage over inductance. Now, the voltage is sort of constant here. For each inductor, the L is constant, so it's going to be a straight line. It's a constant slope. So basically what we are going to see here is that each inductor, the current will start dropping down, and the same thing will go to the other inductor. And when this value here will be equal to this value, it means that the current of L1 is the same magnitude as the current of L2, except that the direction is in opposite direction. And this is exactly what we just said, that the current, say, will go this way in this inductor, and then it'll turn this way for L2, so as to close the loop. And then, of course, there will be no difference, so there will be no current flowing through the Zener diode, and we have this short circuit of the inductor on itself. Okay, now let's see how we translate it into some simple relationship. Again, this is the basic equation, state space equation of the inductor, and from which we find that delta I, that is the change in the current, will be dependent on the slope times delta t. So for the first inductor, we have the initial value minus this drop. This is actually like the current source that I've put in. And here, this part here is the drop. This is the slope, and I'm calling t sub t the total time until equalization is reached. Now, this current should be equal to minus, for the reason I've just said, to I2, this is the original value, minus again the drop due to the constant voltage, call it VL or VZ. Okay, so now we can sort of manipulate these equations, and what we'll get is that the final value for the, say, L1 current is this expression. And sort of reworking it, we end up with this equation for the current through L1, and for the current for L2 is this one here. Well, they look the same, and they should look the same. Now, again, we know that I1 at the end will be minus I2. Now, let's try sort of a quick check to see if we are okay with this equation, and let's have a look at the case in which the currents are indeed already in the right direction, and see what we get. And what we actually get from this equation is that the final value is indeed I1, and the final value according to the equation is I2, which is okay. Now, what about the energies? We know the final value of the current for each inductor. And again, these values should be opposite, same magnitude, but opposite in direction. And again, let's have a look at the case, which is a simple one, just to compare it to the case of the capacitor that we have looked at earlier, in which the initial conditions are such that the inductor current of L2 is 0, and L1 is equal to L2. Well, plugging the value into these equations, we get into the original equation, we get these two expressions, and from which we can calculate the energy of E1, and the same thing will be for E2, because L1 is L2 and I1 is I2, and I squared is the same. So we got, this is for the first inductor, this is for the second inductor, this is the final current. So adding it up, we have this expression here. Now, since we know what is the final value from here, we plug it in, and we see that we get Li1 squared over 4. Whereas at the beginning we had Li1 squared over 2, because there was only one inductor with one current, I1. So again, in this case, we are losing half of the energy in this connection. Let's have a look now at a case which, since we are less familiar with inductors, so this will look very strange, but let's see what is happening in this particular case, in which you have two inductors which are of the same value, same inductance. They have exactly the same initial current. So you can take two inductors, they have the same inductance and the same currents, and you connect them in parallel. Well, if you plug in the values in the equation, you get that the final value is 0. That is, all the energy will be dissipated, nothing will be left. Well, it will be dissipated, of course, in some parasitic resistance that is around, or through a spark. If the voltage will be too high, energy will be removed by a spark. Now, why is this happening? Well, the reason is that in this case, the two currents are the same, the time constant is the same, so that the two currents sort of follow the same line. There is no intersection in terms of one is positive and one is negative, so as to allow a circular current. They are just going down in value until they reach 0, and that's the end of the story. So in this case, all of the energy sort of disappears. Well, at first it looks like very strange. I mean, you take two inductors, they have energy, you connect them, it disappears. Well, not really. Let's have a look at the case of two capacitors which are of the same capacitance, the same voltage, but we connect them in opposite polarity. You see, here is the plus, and here is the plus. This is minus here. So we sort of reverse polarity and connect them. Wow. In this case, just redrawing this thing here, what you have actually is two capacitors in series. You see, if you draw it in this way, you can see that they are actually, the voltages are sort of adding up, and then you put a short on it. What will happen? Now we can use a simplified model for the capacitor, a charged capacitor, which is composed of a capacitance, a capacitor with no voltage across it, plus a voltage source. This is a analog of the case of the inductor that I've shown before, of a inductor plus a current source. Here we have a capacitor plus a voltage source. And so this will be for the first capacitor, this will be for the second capacitor. So we have now two capacitors, no voltage across them, plus a voltage source of 2V. Now, current will flow and charge the capacitor this way. And of course, if they are equal, it'll be the same voltage here. And now I split the 2V back to the two original values and get each capacitor get his original voltage source. And of course you have two opposing voltages, which shows that you end up with a zero voltage on each capacitor. Well, we don't look at it this way usually, but that's the story. That's what happened. And this is very similar to the case of the two inductors which are connected in parallel, having the same direction of a current. So let's just say a few things about the practical differences between the two cases. Now, usually today or these days, the connection between, say, two capacitors will not be with a mechanical switch, rather it'll be an electronic device, say a MOSFET transistor. Now, if you connect two capacitors of different voltage with the MOSFET transistor, there is a limitation of the current. Of course, the current can go very high, and in some cases, actually, it can destroy the transistor. But on the other hand, in many cases, the transistor will tolerate for a short time the high current, and in fact, it'll sort of limit it because it will behave like a current source. So if you look at the current, you'll see that it's sort of being limited, could be fairly high value for a very short period of time, and then it'll drop to zero. On the other hand, if you have the two inductors connected through a semiconductor device, it's going to be a very high voltage. Now, the voltage is going to be extremely high because the difference between the two currents somehow goes through a parasitic resistance, which is the insulation, which is very high resistance, or a spark, which is even worse, meaning that the voltage is extremely high. So you will start up with extremely high voltage, and this could actually destroy the semiconductor devices. So from the practical point of view, engineering point of view, the situation of connecting two capacitors is less dangerous in terms of spikes and harmful effect than in the case of the two inductors. Now we can see these sparks even when we just disconnect two wires. The reason is that a wire will have some sort of a inductance. If it's not a proper inductor, just a long wire has some inductance to it, and if you disconnect it like turn off the light at the switch, you might see a spark coming off, and this is the reason for it. So this brings me to the conclusions, which I can summarize as follows. In the two cases of the parallel collection of capacitors and inductors, there are losses, and there's no escape, unless, of course, the situation is such that there is no need for current flow or a change, but then this is, of course, of no interest. In the inductor, the parallel connection generates very high voltages, while in the capacitor, it's very high current. Now, as I've said, from the practical point of view, the parallel connection of inductors might be more dangerous in practical cases. This actually brings me to the end of this presentation. I thank you very much for your attention. I hope you will find it useful. Thank you.